Okay, let's dive right in. Last time, I showed you we talked about approximation schemes, right? The idea that for certain NP-hard problems, which we cannot find, for which we cannot find exact solutions, we might be able to approximate them as closely as we like. To within a relative factor, a multiplicative factor of as close to 1 as we want. And we, in particular, looked at a fully polynomial approximation scheme for knapsack. Right? Which had a running time polynomial in both n and epsilon, the factor to within which we wanted to approximate. Right? And then I told you, or sorry, what we're going to pick up with today is a not fully polynomial approximation scheme. We are now going to look at a polynomial approximation scheme, a different technique called enumeration. And this is going to be for our old load balancing problem. So we've got m identical machines, n jobs. Job j has processing time pj. Okay. And we're going to talk about how to get an arbitrarily close approximation to the optimum for that. Remember, we have Graham's rule. Which is a 2 minus 1 over m approximation. And I mentioned that longest processing time first is a 4/3 approximation. But I didn't prove it to you because we're going to blow right past that 4/3 and get a 1 plus epsilon approximation using this enumeration technique. Okay? So the enumeration technique, really the place we start thinking about it is Graham's rule, and a little bit about longest processing time, right? People remember the insight that led us to think about longest processing time? Yes, a question? Or?
It was just like, it's bad if the last one is big.
Yeah, it's really bad if the last job is big, right? The problem with Graham's rule is it sort of is if it really does a great job of load balancing everything, and then at the very end, some huge job comes along, and you don't have any place to put it. So that suggests that we want to focus our attention on the larger jobs, right? They kind of influence the schedule. And indeed, if you think about it, if we have a whole bunch of small jobs, we could kind of take care of them later, and they're never going to make things really bad, right? What can you say if the last job that you schedule has size that is very small? What can you say? What can you say about the schedule that you're getting? Right? Suppose that with Graham's rule, that the last job to complete is small. I claim that in that case, we're in a really good situation. How come? People remember? Yes, go ahead.
You can't make things much worse than it is.
Much worse than what?
Than the current state.
What do you mean by current?
Hmm?
What do you mean by current state?
Yeah, before adding the last one.
Good. So before we add, this goes back to how we proved that Graham's rule works well, right? What we said is, you know, let's look at where we added that last job, that one that determines the schedule, right? Why did we add it where we did? Yeah?
It was the one that had the smallest and it first.
Good. We added it to the least loaded machine, right? And what can we say about that least loaded machine? And again, this comes straight from the analysis of Graham's rule. Yeah? Go ahead.
Oh, yeah, its load was lower than average.
Exactly, right? So this last job was added to a machine with load less than or equal to the average. And what's good, what's important, what's good about the average? Yeah?
All tests to take at least the average.
Exactly. The average is going to be less than opt, right? That's one of our lower bounds. Right? So the length of our schedule can actually be bounded by the value of opt plus the size of the last job that we added, right? So if the last job that we add is small, then we're actually very close to the optimum. Yeah?
Isn't it slightly better than that?
Yes, there's a little -1 over m in there, but we're going to be getting an epsilon approximation anyway, so we don't need to worry about that 1 over m anymore. Okay. So does this make clear why small jobs really aren't a problem? Okay, so we only need to worry about big jobs. Okay. So for our next step, let's think about that. If we want to schedule the big jobs, and we want to make sure that we're doing well, why don't we just use brute force? Okay. So the first idea we're going to look at is to schedule the k largest jobs optimally by brute force enumeration. Okay, that's why this technique is called enumeration. It's basically a fancy word for brute force by trying everything. Okay, if we try every possible schedule of the jobs, we will be able to find a schedule where the jobs finish before time opt, right? Okay. Now, what do we do with the rest of the jobs? Well, for the rest, we'll just run Graham's rule, right? Okay. So if we imagine numbering the jobs in decreasing order of size, okay, so we've scheduled P1 through Pk in an optimal way. So what's the worst thing that can happen as we run Graham's rule on everything else? What determines the final value of our schedule? Well, as we've seen over here, the issue is what is the job that got added that determines Cmax, right? And the worst case is if that job that we add that determines Cmax is the next biggest job, namely Pk plus 1, right? So the worst possible outcome is if Cmax is determined by adding job k plus 1 to the least loaded machine at the time. Right? Just by what we said over here, that our Cmax is going to be opt plus whatever the last job we add is. So in other words, the the Cmax that we get is going to be at most opt plus pk plus 1. Right? So all we need to do is relate pk plus 1 to opt. Okay? So how can we do that? Well, notice that P1 through pk are all at least pk plus 1. By the way, we've indexed the jobs, right? Which means that the average load is at least k plus 1 divided by m times pk plus 1, right? I've got that much work. And the average load is also a bound on opt, right? So we can say that opt is at least the average load, which is at least k plus 1 over m times pk plus 1. Yes? And that in particular means that pk plus 1 is at most m over k plus 1 times opt. So we can go back and plug that into the formula that we have over here, and we discover that our Cmax is at most opt plus, or opt times 1 plus m over k plus 1. Right? What does that mean? Well, what it means is that as we make k bigger and bigger, we get a better and better approximation to opt. But what's the downside of making k bigger and bigger? Yes? Right. The problem is the runtime. So how long does it take for us to brute force all possible solutions? Yes? And to the k, how come? Exactly. For each job, we have to pick a machine ID. So we have k jobs, and each of them there are m choices. There's some, you can save a little bit by recognizing that there are symmetries, right? You can always make the first machine the busiest one and not try all the cases, but it's not really, it doesn't really gain you very much. So the runtime is going to be that there are m to the k different arrangements of choices that you have to make, right? And then, of course, for each of those arrangements, you actually do need to schedule the other jobs in order to decide what the overall runtime of the schedule is going to be, right? If you really want to optimize things. I mean, in fact, if you just find the minimum arrangement of the first jobs, it doesn't actually matter. Like, you'll still be within this target. So you could settle for just doing the brute force enumeration and then just adding the other jobs. And this might not be the best possible enumerated schedule, but it will be a good enough enumerated schedule. Okay. So is that polynomial? Well, it kind of depends. You see, if you look at the definition of the problem, right, when you say that there are m identical machines, you only need log m bits to say that, right? You don't actually need to put a list of m different machines into the input, because all you need to describe them is how many there are. So m doesn't, you don't really want to think about m as being a part of the input, right? But even if m is 2, even if m is small, or if you do want to think of m as part of the input, you've got a problem because k is in the exponent, right? So as you grow k, things are going to get very slow. But what we can say is that sort of looking at these two things together, we do have, for any fixed m, okay, 3 machines, 4 machines, whatever, we do have a polynomial approximation scheme. Okay, what we do is we set epsilon equal to m over k plus 1, because we're looking for a 1 plus epsilon approximation scheme, or 1 plus epsilon approximation, right? Which tells us that k is about m over epsilon. And then we can just go and plug that in over here. And our runtime for getting an epsilon approximation is m to the m over epsilon power plus n. Yes? So as long as m is small, we have a polynomial approximation scheme. Unfortunately, if m is large, m is also showing up in the exponent, right? And so this no longer satisfies the definition of a polynomial approximation scheme. Okay? So we got something, but not enough. Everybody understand what we did here? Okay. So how can we make it a little better? We're going to take the same general idea of sort of brute forcing the large machines, but we're going to think about how to be smarter about our brute forcing. Okay? So the next idea is, instead of just thinking about the k large jobs as the thing that matters, suppose that there are only k distinct job sizes. Okay? So we're going to figure out how to brute force this situation. So this is better, right? Instead of being limited to k actual jobs, we can have many jobs as long as a lot of them are of the same size. Okay? And I claim that we can figure out an optimal schedule for these jobs, of which there can be n, right? So we're going to allow a large number of jobs now, but they have only a small number of distinct sizes. I claim we can still figure out a brute force optimum. Okay. What we're going to do is we're going to define, we're going to characterize a machine by a vector. So per machine, we're going to imagine that we're going to describe it by a vector of how many jobs of each size it runs in a particular solution. Okay? And we will call this the machine type. Okay. And we will now characterize actually, before I go on, how many different types of machines are there possible? That is, how many different ways could you write down a vector which describes a certain number of jobs of each size? Yes?
At most n over k to the k.
Right, or n over k to the, yeah, it's one of these partitioning, right, from 6042. But I'm going to be sloppy, right? So essentially, we have a vector of k entries, each of which can be between 0 and n, right? How many jobs of that type you're running, okay? And that means that there are n to the k at most types, right? So what's nice about this is that if that k is constant, this is a polynomial, right? Polynomial number of possible machine types. Okay. Notice that there are also only n to the k problem instances for the same reason, basically, right? A problem instance is how many jobs of each size do you want me to schedule? So it's also described by a vector of k numbers between 1 and n. Okay. So now I'm going to go back to something I did with Knapsack. I'm going to think about the decision problem. Can I schedule my given input in time at most t? Okay. I claim if I can solve this decision problem, I can optimize using what? Binary search, right? So this is just a simplification to let us focus on the decision problem. And how might I solve this decision problem if I'm focused on these different machine types? Well, what I'm going to do is use a dynamic programming. To answer the following question. Which instances can be solved in time at most t using some number r of machines? Okay? And I'm going to remember there are only a polynomial number of possible problem instances. So I'm just going to list all the ones that are solvable in the target time. Okay? So let's think about this. Well, we know which inputs can be solved with 0 machines. That's not very interesting. How do we figure out which instances can be solved within time t using 1 machine? Yeah?
Like, so if you take an instance, you like say you say for each job size how many that job size you do, and you add it up. Exactly. It's less than or equal to t.
Exactly, right? And this is a list of jobs. We just see if those jobs use more than t time, right? And essentially that's equivalent to saying on 1 machine, right? Well, the solvable instances are equivalent to machine types that take less than t time in total, right? A machine type is, again, a specification of running a certain set of jobs. If they take less than time t, that set of jobs is an instance that you can solve in time less than t. Okay. Now the dynamic programming part, right? Suppose you know all instances solvable on R machines. How do you find instances solvable on R+1 machines? Right. If an instance is solvable on R+1 machines, I'm looking for some kind of optimal substructure that I can leverage in a dynamic program. Right. Yeah? Right. And if you, well, be careful. We can brute force over how many of each size we'll have on the last machine, which is basically brute forcing over what is the type of the last machine, right? And so basically, any solution with R+1 machines has one machine that's the last machine. And so it is a collection of R machines that solves some set of jobs plus one machine that solves some more jobs, or that does some more jobs, right? So all we need to do is combine every instance solvable on R machines with any one machine type. Right? We take any set of jobs that can be solved on R machines, and we add the jobs from one more machine that can also be solved in time t. Make sense? And how long will it take us to do this? To consider every possible combination of a solvable instance on R machines with one more machine type. Yeah? And to the decay.
Because there is an overlap in decay.
Exactly. Time is, at most, the number of instances. We're looking only at the instances that are solvable with R machines, but that's bounded by the total number of instances, times the number of types, which, as we've already seen, is at most n to the k times n to the k, or n to the 2k. So, as long as we have k distinct job sizes, and it doesn't matter what they are, right? If there are k distinct job sizes, we can get an exact solution by this simple brute force enumeration of all solvable instances, plus binary search. Okay? So I've got my people who are answering pool is a little limited. Have I lost people, or is it all making sense? You're lost. Ask a question.
So then first, we're taking like the job sizes and just like turning them into k distinct.
No. Right now, what I'm doing is assuming we start with k distinct sizes. Okay. Now, if I want to be able to solve an arbitrary scheduling problem, I'm going to have to reduce that case somehow. I haven't shown you how to do that yet.
What does it mean, like I don't think I got the DP transition.
Good. So, are we agreed that it's pretty easy to figure out which instances can be solved on one machine? Okay, so how do we figure out which instances can be solved on two machines? Well, we basically need to take any two machines and put them together, add up their jobs, and that's an instance that can be solved on two machines, right? So we basically, and so we take the combination of any two machines, and that gives us an instance that can be solved on two machines. Now, if we were really going to brute force things, we could also talk about taking any combination of three machines and combining their jobs. But then you're going to start getting this sort of exponential growth. So what we do instead is they say, to figure out how to solve jobs on three machines, well, we know that the first two machines solve a subset of the jobs. So let's look at all of the subsets of jobs that can be solved on two machines and combine each of those subsets with one more machine. Okay? And the point is that the number of subsets that can be solved on two machines, the number of instances, right? An instance is just a collection of job sizes, right? The number of instances that can be solved on two machines is less than the total number of possible instances. And one of the first things that we argued was that there are only n to the k problem instances, right? So we take we take each of these solvable instances on two machines, of which there are most n to the k. We imagine combining it with each possible last machine, which is going to solve some more jobs. We combine those jobs, and that gives us an instance that's solvable on three machines. Okay? And that, again, is a set of at most n to the k instances. So for the next iteration, we try adding one more machine to get things that can be solved on 4 machines. A question?
One question. For each of the instances, we only have a subset of jobs, right? Like, we aren't guaranteed that there's a certain number of jobs that are covered in the machines.
That's right. I mean, again, the definition of an instance is that it is a certain number of jobs of each size, right? And some of those instances are solvable within our time bound on 3 machines, and some are not. And we figure out what that distinction is. What is the set that are solvable? And then we use that to build the set of instances that are solvable on 4 machines. Okay. Yeah? I'll come back. It's still not clear, but maybe there's another clarifying question.
If we try instances that are solvable on up to the k machines.
So good idea, right? So if the number of machines we want to use is a power of 2, right? Then you could say, well, anything that's solvable on 4 machines can be solved with 2 machines and 2 other machines. So I look at what can be solved with 2 machines, I look at and I sort of put those together twice, and that gives me all the things that can be solved with 4 machines, right? What was that? Right. So if it's not a power of 2, you can now sort of combine the different powers of 2 that you need to make a certain number of machines, right? And so if you think about it, that is going to save you time, right? So what we're doing now costs us sort of this n to the 2k time to add each machine, right? And we're going to have to add a machine m times, right? So overall, the runtime of this thing is going to be m times n to the 2k, right? Because we add a machine m times. If we use what you're proposing, that m goes away, right? Well, if we want to build a power of 2, it will only cost us log m of these squarings or doublings to get a power of 2 machines. And once we have all the powers of 2, we can put the appropriate powers of 2 together in order to get the number of machines that we actually want. And so that also will only cost us another log m sort of combination steps. So you will turn this m into a log m. So that would be an improvement, yes. However, the thing that's really killing us in the runtime is this n to the 2k, right? Usually we think of m and n as comparable, and so you're making it n to the 2k instead of n to the 2k plus 1. Okay. So has everybody gotten things clarified to where they need now? Great. All right. So as we were discussing, this lets us deal when all of the sizes are coming from a small set of possible sizes. How do we solve the general case? What do we do if there's lots and lots of different sizes? Yeah, you have a thought?
Search time.
What's that?
Binary search time.
Well, we can binary search the target completion time. That is what we do here in order to optimize for it. But that by itself isn't going to change the number of different job sizes that we have to deal with. Yes?
For job sizes?
What kind of scaling are you thinking about?
I'm not quite sure, but like if we can reduce the number of job sizes by like scaling each of them, then should that? I don't know how to go from one.
Yeah, how do we build on that idea?
Group job sizes into things and like have a representative size to be the max.
Yeah. Like if you think about it, jobs that are about the same size, we're approximating anyway, right? So if jobs are about the same size, we can probably treat them as being the same size, right? So it's basically the kind of rounding off and scaling that we did for knapsack, right? We're going to use rounding, right? So once again, I'm going to guess the optimum, and imagine the binary search that's happening, right? And I'm going to solve the decision problem. So now all I want to know is, can I solve everything within time t, or I'm going to guess that the optimum is t, and I'm going to try to get close to t in my solution, right? So what I'm going to say is that jobs of size larger than epsilon t are what I will call large jobs. Okay. So these are jobs. Notice that if the optimum is t, no job can be bigger than t, right? Because it won't fit. So now what I'm going to do is round each job size up to the next power of 1 plus epsilon in this range between epsilon t and t. Okay. So I'm only going to look at powers of 1 plus epsilon in this range. And those are going to be the job sizes I actually work with. And I'm just going to make every job a little bit bigger. So what's the worst case change in a job? Well, since I'm rounding up to powers of 1 plus epsilon, each time, or each pj, is multiplied by, at most, 1 plus epsilon, right? So in order to do this rounding, I don't have to change any of the pj's very much. And that means that opt increases by, at most, 1 plus epsilon, right? OK, so this made a small change in the possible opt that I can achieve. How many different values do I now have that I've done, now that I've done this rounding of these large jobs? Yeah?
You said opt increases by that much. Is it a factor of that much?
Yes, these are both multiplicative, right? So let me put that here. Okay. Yes?
T 1 plus epsilon?
Yeah, the point is that I'm taking powers of 1 plus epsilon. How fast, or how many do I need to take to grow from epsilon to t? There are log base 1 plus epsilon of 1 over epsilon such values in this range, right? Number of times you need to exponentiate 1 plus epsilon to get 1 over epsilon. And this is approximately equal to 1 over epsilon log 1 over epsilon. Okay. So what's important is that for any epsilon, this is a constant. There's a constant number of job sizes. Okay. We know now how to brute force the rounded jobs to get an optimal schedule of the rounded jobs. Okay. The time that it takes is n to the 2k, where k is the number of job sizes. We've said that the number of job sizes is 1 over epsilon log 1 over epsilon. So the time is m times n to the 2 over epsilon log 1 over epsilon. Yes? And we get an optimum for the rounded jobs. And how does that compare to the original optimum? Yeah? One thing at a time. So how good is the optimum that we've rounded the jobs and we get an optimum. How good is that optimum? Yes. Exactly. I actually said it right here, right? So 1 plus epsilon times t. Okay, so all of the big jobs, we can schedule them in time 1 plus epsilon times t. Okay. Now we have to schedule the small jobs. How do we do that? Yeah? Yeah. So small joules using grams rule. How much does that add to the schedule? The answer to that question is also on the board, or a board. Yes? Exactly, right? This adds, at most, the maximum small job to the completion time, right? If you want to break it down farther, there's really two possible things that might happen. One is that Cmax is left unchanged because all the small jobs went into the holes in the schedule, and the last job is actually one of the big jobs. In that case, you're still at this optimum. The other possibility is that you add so many small jobs that you go up. But if you go up, we argued over there that you go up by at most the last job that you added. You go above the original opt by at most the last job that you added, right? So that means that you are adding at most another epsilon t, right? Because the small jobs, the only jobs we have left are of size at most epsilon t. Okay? So that means that overall, your completion time Cmax is at most 1 plus 2 epsilon times t. Yes?
Doing them both separately? I feel like it would just be epsilon if you did, like, for each brute force thing, you, on top of that, you, like, did grams rule.
Well, the problem is, again, that when you brute force, you may get something that's already off by epsilon, right? And then grams rule, actually, I think if you argue it carefully, right, and sort of what happens, like depending on whether you go past where you started or whether you stay at where you started, I think you can argue that in either case, it's going to be at most 1 epsilon, that they don't add.
Yeah, but I guess if you wanted to do, like, over there, you're talking about how you can either do a multiplicative runtime or an additive runtime. Like, you can schedule the small and the large ones separately.
That's right.
So if you do small and large separately, I guess, then you would be...
Yeah, I think if you're careful, you can get 1 epsilon, right? But algorithmicists are always sloppy. That's why we invented the O notation, right? And so in particular, here, it's just a factor of 2, right? Which we can fix by making epsilon half as big. So we won't worry about it, okay? And so now we're done, right? We have found a solution which is within 2 epsilon of optimal. The runtime comes from the brute force enumeration that is dependent on 1 over epsilon. So you'll notice that for any fixed epsilon, this is a polynomial in M&N, right? It's not polynomial at epsilon. And that makes this a polynomial approximation scheme and not a fully polynomial approximation scheme. Okay. All right. So what I've showed you now is that we can get as close as we want to on PCmax. This problem, PCmax, there's actually sort of a complementary problem called the bin packing problem. So in bin packing, you're not told you have this many machines, how fast can you finish? Instead, you're told you have this much time, how many machines do you need, right? Or more generally, I have a number of items of different sizes, and I need to put all the items in boxes of size 1. You can always scale everything to 1, right? How many boxes do I need? Okay. And that bin packing problem is, in some sense, it's been around longer. It's sort of considered more elegant and poetic than the PCmax. There's been a lot of work on bin packing. It's a question of whether you flex in the size of the boxes or the number of the boxes, right? That's the relationship between them. But this technique is also the technique that was used to give polynomial approximation schemes for bin packing. Okay? And that you will find on your homework this week, right? How is sort of tweaking this to manage the number of boxes instead of their size. Okay? All right. So now we've seen a bunch of approximation algorithms with specific factors, and we have also seen that there are some problems that can be approximated as closely as you want to 1, okay, within any constant factor. Obviously, we would like to know for a given problem which category we're in, right? Oh, actually, sorry, let me say a little bit more about enumeration. I told you with respect to fully polynomial approximation schemes that they had this sort of tight connection to pseudo-polynomial algorithms, right? We saw that how you can go back and forth between them. If you have a fully polynomial approximation scheme, you can make a pseudo-polynomial algorithm, and vice versa. And that I said that there's sort of this complexity theoretic paper that says that really that's the only way to build a fully polynomial approximation scheme is through dynamic programming on the rounded instance. There's a similar complexity theoretic paper that says that really this is the only way to make polynomial approximation schemes, is by the sort of brute force enumeration of some part of the problem. The definition of enumeration is complicated, and so they have to use a lot of words to define exactly what they mean, but that's the general gist of what they're trying to argue, is that this is the fundamental way to create a polynomial approximation scheme. Okay? So now back to, we've got some problems that can be approximated arbitrarily closely, like the ones we've just seen. And others cannot. The complexity theorists have developed a lot of machinery and have defined something known as max SNP hardness. So problems that are max SNP hard, they can be approximated to some constant factor. But not to arbitrary constant factors. So they do not have polynomial approximation schemes, and certainly not fully polynomial approximation schemes. So for example, one of the problems that we looked at earlier was vertex cover, and that problem is max SNP hard. There is no approximation scheme for it. Okay? In fact, they've shown that you cannot beat 1.001. I think. They may have improved that recently. Okay? But you cannot get better than 0.1% approximation for vertex cover. And so this is an interesting fundamental difference. We're all a lot of it is a theoretical difference because obviously in practice that 2 over epsilon in the exponent is going to make your algorithm pretty slow, pretty fast. And so it may not be useful in practice, but there's some beautiful theory behind it. Okay. What's also interesting is that if you use this machinery to prove that you can use this machinery to prove that certain constants are out of reach. If you combine that with an amplification technique, can be used, right? Amplification is something we do with additive approximations, where we said if you can approximate to within a certain factor, then you can also approximate to within a better factor, right? Well, you can use the amplification technique to show that some problems have no constant factor approximation. Okay. Basically, you show, this problem cannot be approximated to within 1%, and then you also show that if it can be approximated to within any constant, it can also be approximated to a better constant, right? And so if it can be approximated to any constant, then you can keep making the constant better and better until it beats 1%, and you're violating the max SNP hardness of the problem. And so, for example, the independent set problem is a problem that cannot be approximated to within any constant factor. Because if you did, you would be able to approximate it past its hardness boundary. Okay? And you can, I think I give you that amplification, the problem of amplifying independent set on this week's homework, if I remember correctly. Okay? All right, so that's the story of approximation schemes, dynamic programming, brute force enumeration. Any questions? Yes, a question. Okay, any questions before we take our break? Good, so you should relax extra hard today because afterwards we're going to study relaxation. Okay.
Extension we can put for if we do we still put before Friday if we do before Saturday at 2 or something?
What?
There's the extension, right?
Yeah, we haven't changed the extension deadline for this PSET. It's just that we just put in extra time for getting it in on time.
Okay.
All right, let's get started on our relaxation exercises. So we are now going to study the next important technique in approximation algorithms, known as relaxation. Very important for MIT students to study this. The idea here is that when we're faced with, like so far we've been sort of saying we're faced with this problem that comes with certain constraints that we have to satisfy. And we've sort of sacrificed some on the objective in order to satisfy all of those constraints. The idea of relaxation is given a problem with difficult constraints, we will remove some of them or reduce some of them. To make the problem easier. Okay, and that's all there is to it, right? Once we take away a bunch of the constraints and the problem's easy, we can solve it. Okay. Now, what's going to happen when we do that? What goes wrong? Yeah? Exactly. So we get an infeasible solution. And that takes us to the final step, which is we need to somehow round that infeasible solution to a feasible one. in a sense, we remove some of the constraints, but we try to keep enough of them so that the solution to the looser problem, to the relaxed problem, sort of gives us guidance about how to home in on a solution to the original problem, right? And so the goal of this rounding is to not change the objective too much. Okay. You'll notice that we are removing constraints, right? So we get this infeasible optimum, which is better than the true optimum. Because all we've done is, if you remove constraints, it lets you improve on your objective. Okay, it doesn't make it harder. So if we are able to get a feasible solution that is close to our infeasible optimum, then that feasible solution is also going to be close to the true optimum. In other words, it will be a good approximation. Does that make sense? Okay, so this technique is used all over the place, and the creativity is not in coming up with the idea of using it, but in figuring out what constraints can you loosen. And again, the key is if you take away all the constraints, it becomes trivial to solve the problem, but the answer doesn't tell you anything. So you want to loosen the constraints as little as possible so that the answer gives you as much guidance as possible, and it's easy to round back to feasibility. Okay. And so as a first demonstration of this, we're going to look at one of the most famous NP-hard problems, the traveling salesman problem. Okay. So this is a storied in myth and legend kind of problem. You have a graph. You have edge costs. And what you want to find is a tour that visits every vertex exactly once and returns to the start. And the formal term for this is a Hamiltonian path, Hamiltonian cycle. And what you want to do is minimize the cost, the edge cost of this tour. Okay? Now, framed this way, there's kind of a deep problem with talking about approximation algorithms, which is that even without edge costs, this is NP-hard. Okay? Just finding a tour that visits every vertex exactly once is NP-hard. There might not be one. And it's NP-hard to decide if a graph is Hamiltonian or not. Okay? So this is not the kind of problem that we work on approximating. But there is a special case called the metric TSP, where the edge lengths form a metric. Okay. Or equivalently, it is a problem where you're required to visit every vertex at least once. Okay. Why are these equivalent? Well, if you start with a non-metric graph, you can create what's called the metric completion. Basically, you put an edge between every pair of vertices whose length is the shortest path in the original graph. Okay? So that turns your graph into a complete graph, right? If the edge lengths form a metric, then by definition, you have to have a complete graph because there is a distance between every pair of vertices, and there's going to be an edge representing that distance. Okay? Now, on a complete graph, it's trivial to find a Hamiltonian tour, right? Any sequence of vertices is a Hamiltonian circuit. So once you made the graph complete, you can actually look for Hamiltonian circuit. But the point, and once you find a Hamiltonian circuit in the metric completion, you can go back to the original graph, right? Anytime you're traversing an edge in the completion, that corresponds to traversing a path in the original graph, right? And so if you have a series of edge traversals that visits every vertex, well, if you turn those edge traversals into paths, you're still visiting every vertex. You just might be visiting some vertices more than once. Okay? So in the metric TSP problem, it's easy to find a feasible solution, and the only question is how costly. What will its cost be? Okay. Now, this problem is max SNP hard. So we will soon see that it is approximable to within some constant, but that it is also not approximable beyond some other constant. Right? In fact, even what's called the 1-2 TSP problem, where the only edge lengths are 1 and 2, is max SNP hard. Okay? You can think about why this is always a metric if you have a complete graph with all edge lengths 1 or 2. Okay. Let's look at how we can get an approximation to the traveling salesman problem using relaxation. So what will make a plausible relaxation of the traveling salesman problem? The goal of the traveling salesman problem is to kind of join up all the vertices through a single path. But that's a really complicated constraint to think about. As I said, finding Hamiltonian paths is challenging. Can you think of other problems that involve joining up all the vertices in a cheap way? Yes. Minimum spanning tree. Okay. So I claim that the minimum spanning tree problem is a relaxation of the traveling salesman problem. Okay. With a little fudge, right? The point is that if I leave off one edge from the Hamiltonian circuit, right, then what's left is a path, which is a special case of a spanning tree. Right? So the TSP minus one edge is a path, i.e. a tree. Okay. And that tells us that the minimum spanning tree is cheaper than the optimum traveling salesman tour. Okay? So we basically do away with the path constraint. We keep the connect everything constraint. Okay? So we're only loosening constraints. We're not adding any new constraints. Okay? So this is a relaxation that was discovered very early. The hard part is figuring out how to round it. So here is the minimum spanning tree. How could we use the minimum spanning tree to define a good tour that doesn't cost very much? Let's think about it. If all you know is the minimum spanning tree, how would you plan your tour of the graph? Yeah?
Euler tour, tree
Yeah. I mean, basically, I would do a depth first search of the graph, of the tree, right? How far do I travel in a DFS of the tree? Yeah?
Edge at most twice.
Exactly. I go down every edge, and I go back up every edge, right? Okay. And so the cost of taking this tour is just equal to twice the cost of the minimum spanning tree, right? But we already argued that the minimum spanning tree is a relaxation of the traveling salesman problem, so the cost of this tour is at most twice the cost of the optimum traveling salesman tour. In other words, this very simple algorithm is a two approximation. Any questions? All right. Well, this was so easy that nobody got their name attached to it. But a guy named Christophides figured out how to make it cleverer. This happened sometime in the 70s. I don't remember exactly when. Oh, sorry, I should be clear here. This is an undirected graph. Okay, we don't really talk about minimum spanning trees of directed graphs. Yes?
Metric TSP.
Yes. All of this, so as I said, non-metric TSP, we can't talk about approximation because we can't even necessarily find a tour. Okay, so everything I'm going to be telling you about is for the metric case. So what did Christophides do? Well, Christophides looked a little bit deeper at what we are doing in the rounding step, right? So I said just do a DFS and that visits every vertex twice. But if we look at the minimum spanning tree, okay, we're trying to navigate this minimum spanning tree to visit every vertex. We don't necessarily have to do a DFS because we do have a metric and we can take shortcuts. Sorry, is there a question?
No, not the question.
Oh, okay. So if we imagine that we might want to take shortcuts that jump across different places from the tree, right? If we sort of trace out our tour, right? We may go down to here, but then we say, well, our next step is to go to this vertex, so let's just go straight. Okay. And then we continue, we go up here, and now we go back down, and now maybe we'll go this way. Okay. And we can basically shortcut lots of parts of the, whoops, not that, because we're going to want to visit this guy. Then we'll go here. So here I've put some shortcuts in to the depth first search, right? Now, if I look at the edges that I've added representing shortcuts, they've done something important to the graph, right? And you already used the right phrasing of Euler tours, right? So if I'm actually going to be able to visit every vertex of the graph, right? Every entrance also has an exit during those visits, and that means that the degree of the edges that I use has to be, the degree of every vertex in terms of the edges that I use has to be even, okay? So if you think about it, when I was doing the depth first search, if I wanted to actually trace the edges I needed to use, I would be putting 2 copies of every edge, one for going down and one for going up. And that would make every degree even, obviously, because all of the edges are doubled. But what Christophides said is, you don't have to use that way of making the degrees even. If you add edges in a way that makes all of the degrees even, then you will have what's called an Eulerian graph, where all the degrees are even, okay? So you need to add edges to the minimum spanning tree to make it Eulerian. In other words, all degrees even. And if a graph is Eulerian, then that graph has what's called an Euler tour that crosses each edge once. Exactly once. And will therefore provide us with a traveling salesman tour of the entire graph. Okay? So Christophanides said, yes, start with the MST, but instead of just taking depth first search, let's look for the cheapest way to make the graph Eulerian, to make the MST Eulerian by adding some more edges. Okay? Now, what is that algorithmic problem? Okay? You'll notice that I only had to add edges to some of the vertices, right? Which vertices did I need to add edges to? Yeah?
Odd degree vertices.
Exactly. I only add edges to the odd degree vertices. Okay. And I claim that, I mean, I'm going to have to add an edge to every odd degree vertex, right? But that means that I never need to add more than one edge to any odd degree vertex, right? That would be overkill. I just need one edge to make it even, right? So in fact, we only need a matching between the odd degree vertices. And so what Christophanides says to do is the obvious thing, which is to use the min-cost matching as your way to complete the minimum spanning tree into an Eulerian graph. Okay? Reasonable thing to do? Notice this means this shows you that every undirected graph has an odd number of, sorry, has an even number of odd degree vertices, right? Because they have to be they need to be matchable in this way. Sorry, it doesn't show you that, but the handshaking lemma tells you that there will be an even number of odd degree vertices, and that means that their matchings will exist. So the only question that remains is, if you do this, how good is it? Right? So now, I should mention, this is not the bipartite matching problem, right? You now have a graph, a complete graph, and you can match arbitrary pairs, but they're all the same. They're not two different sets of vertices. So the algorithm that you studied earlier based on flows cannot be used to compute a min-cost non-bipartite matching, but there are polynomial time algorithms for non-bipartite matching. Okay? And they are also based on augmenting paths. They're just a little bit more complicated. So we're left with the question of how costly is the min-cost matching? Okay. So for that, let's consider the optimum tour. Okay? So I'm going to draw the graph. Okay. Sorry, let me put in a couple more vertices. Okay, so here we have the optimum tour. I claim that from the optimum tour I can get a cheap matching. Okay? So first off, we are going to ignore the, let's shortcut all the even vertices on this tour, even degree, from the minimum spanning tree. So if I leave out all of the even degree vertices, 1, 2, 3, 4, 5. I need to make sure I have an even number of odd degree vertices. So by adding shortcuts, I can create a tour on the odd degree vertices. Yes? OK, where's my cheap matching? Yes? Every other edge. Forms a matching. Right? So I can label every other edge, say that's matching A. Instead, I could take the other edges. That gives me another matching B. Right? So in fact, we have 2 disjoint matchings form the tour. Okay. But we created that odd vertex tour by shortcutting in a metric, which means that the total length is less than the whole tour, i.e. the length of the TSP. So we have 2 matchings that together add up to less than the TSP tour, or at most the TSP tour. That tells us that at least one matching is at most half of the TSP. Right? Which means that the min-cost matching is less than or equal to half the TSP, which means that Christophanides builds an Eulerian graph of cost at most, the minimum spanning tree, plus half of the TSP, which is at most 3/2 of the TSP. So Christophanides heuristic gives us a 3/2 approximation to the traveling salesman problem. Yes?
And create
So the point is that in order to make this graph Eulerian, we need to create a matching on the odd degree vertices of the minimum spanning tree. Okay? Now I need to prove that that matching is cheap. So I'm doing a thought experiment. I'm saying, how would I make a cheap matching on the odd degree vertices? What I do is I start with the optimum tour. This also has even degree vertices on it. Every time there's an even degree vertex, just toss it out from the tour and use a shortcut that skips over it. Okay? Now, it's a metric, so this shortcut is cheaper than or no more expensive than going via the even vertices. So I end up with a tour that only visits the odd vertices, but I haven't increased its cost. So this odd vertex tour costs less than the original traveling salesman solution. Okay. Now notice this is a thought experiment. I don't actually know what the optimum tour is, but I'm just proving the existence of a cheap matching, which proves that when I look for a cheap matching, I will find one. I won't necessarily find this one. Okay. Any other questions about this very nice 3/2 approximation algorithm? No? Okay, I'll mention a few closing remarks about TSP. One is that there has actually been recent progress that has broken 3/2. A lot of it happened right here at MIT. Alex Madry and others, Michel Gomans, have made really important progress on the traveling salesman problem. There's also been progress with what's known as the Euclidean TSP.